Imagine two doors. One is light and narrow. The other is heavy and wide. You apply the same force to both. But one door swings easily, while the other resists motion. Why does this happen? The answer lies in a powerful mechanical concept called moment of inertia. Welcome to Chapter 1 of Properties of Bodies, where today we build the foundation of rotational mechanics. If you truly want to understand shafts, flywheels, gears, turbines, cranes, and rotating machines, you must understand moment of inertia. In engineering mechanics, properties of bodies tell us how an object behaves under force, motion, rotation, bending, twisting. And the very first rotational property we study is moment of inertia. Think of it as mass for rotational motion. Just like mass resists linear motion, moment of inertia resists rotational motion. Moment of inertia is the measure of a body's resistance to angular acceleration about a given axis. In simple words, it tells us how difficult it is to start or stop rotation of an object. Key point to remember: moment of inertia is not fixed. It depends on axis of rotation. Think about a spanner. Hold it close to the nut and rotate easy. Hold it from the far and difficult. The mass didn't change, but distance from axis increased. That distance effect is everything in moment of inertia. For a single particle, moment of inertia I equals m times r squared, where m equals mass of the particle, r equals distance from axis of rotation. For a complete body, I equals sum of. This means more mass, higher inertia. More distance, much higher inertia. If mass is located far from axis, moment of inertia increases rapidly. This is why hollow shafts are better than solid shafts. Flywheels store energy efficiently. Wheels have rims. Turbines spread mass outward. SI unit, kgm². This tells us mass distribution, not just mass. Mass, linear motion, depends on quantity, same everywhere. Moment of inertia, rotational motion, depends on distribution, changes with axis. Same body, different moment of inertia for different axes. Let's look at some important engineering bodies. 1. Thin rod. About center, I equals ml². About one end, I equals ml². 2. Solid disk. About center, I equals mr². 3. Hollow ring. About center, I equals mr². Notice, hollow ring has higher inertia than solid disk of same mass and radius. Moment of inertia directly affects starting torque, stopping time, energy storage, vibration resistance, stability of rotating systems. In real plants, flywheels smooth load fluctuations. Shafts resist torsion. Rotors control speed stability. Cranes prevent sudden jerks. This is not theory only. This is industrial reality. Rotational kinetic energy, Ke equals 1/2 I omega squared, where omega equals angular velocity. So energy stored depends on moment of inertia, speed of rotation. That's why flywheels are designed carefully. Common mistakes students make: confusing mass with moment of inertia, ignoring axis of rotation, forgetting our superscript 2 effect, using wrong formula for body shape. Always ask about which axis. Which has higher moment of inertia? Solid shaft or hollow shaft? Answer: hollow shaft. Why? Because mass is farther from axis. Let's recap Chapter 1. Moment of inertia resists rotation, depends on mass and distance from axis. Axis matters. Units are kgm², essential for rotating machinery. This concept will follow you into torsion, flywheels, gears, vibrations, dynamics of machines. In Chapter 2, we will explore radius of gyration and how it simplifies moment of inertia calculations. If this chapter helped you see rotation differently, hit like, subscribe to the channel, and share it with a fellow engineer. This is Simple GAN, where engineering is made simple, visual, and practical. See you in the next chapter. Keep learning, keep rotating. Pure fire.